It's great to be back here at Colaba. So today I'm going to speak about a particular class of integrable models called the Calogero family of models, and various aspects of it in terms of nonlinear dynamics and solitons and collective field theory of these models. So my association with classical integrable models sort of has been in two directions. We have been interested in finite dimensional systems, the Calogero particles, and I'm going to discuss the idea of solitons for finite dimensional systems. By finite dimensional, I just mean n particles in 1D or something like that. And then a dual representation of these finite dimensional systems, and generally the idea of nonlinear dynamics quenches and some universal properties that is shared by many of these finite dimensional systems. On the other hand, I've also had some interest in continuum systems like PDEs. For example, the Quadratic de Vries equation, which appears in the context of cold atomic systems. It's an integrable PDE, and it appears in nonlinear optics also, and also a non-local partial differential equation. So it's a continuum system, and it's called the Benjamin-Ono equation. And there are also multi-component PDEs like the NLS, multi-component nonlinear Schrödinger equation, and the KdV systems, which also are integrable, and some versions of it might appear in cold atomic systems. And even there you can talk about quenches, solitons, and so on. So there is some, in my talk, there is some sort of a connection we'll try to make with finite dimensional systems and infinite dimensional systems, but in this talk I'll only focus on this part. And many of my results I'll be presenting is with Polychronakos and some older papers. So I'll be only talking about classical integrability. So just to set the stage, for my purposes, I'll just define classical Liouvillean integrable systems. So a state of system with n particles, if you have n particles, then you have 2n dimensional phase space, n positions, n momenta. And so when do we call this integrable? We call this Liouvillean integrable if it has n independent conserved quantities. Okay, so Hamiltonian can be one of them. So this is what we would call Liouvillean integrable. So you start with n particles with some interaction. If I can define n quantities which are conserved, then the system is integrable.
Capital N and little n, there is no relation between the two?
Sorry, this is also capital N.
Little n independent, did you mean capital N?
This is capital N, yeah. This is capital N.
Basically as many conserved quantities as
the degrees of freedom. Exactly. So just a trivial example would be just sum of n harmonic oscillators. This is again capital N. And n conserved quantities could just be pi square plus qi square. So that is just conserved. Okay. So but we'll see that when we talk about interacting systems, you can have very interesting systems, and you have these n conserved quantities, and Calogero will be the main thing that I'll talk about. Sorry? Yeah, I mean, so some you can talk about models where you can just generate integrals of motion, okay, n integrals of motion by some mechanism, and then you can just say that that's integrable. All of them may be Liouvillean integrable, but I mean you can have different notions of classical integrability. But I mean, for example, existence of a Lax pair, as I will discuss. Yeah. So I mean, but the point is that if you have Lax pair, if there exists a Lax pair, then the system is integrable. So that's
basically it is always the case, no matter what the definition, that you have as many quantities whose Poisson bracket with the Hamiltonian vanishes as you have
degrees of freedom. Yeah, that's what we'll define as integrable model.
I mean, even in the other machine.
Yeah, I mean,
in the end, is it
irrespective of the things, at the end of the day, you can always write down the right.
Yeah.
But I think what you're saying is that whether or not you can say something is integrable
Exactly.
Your diagonal function does not coincide with
For classical integrable models, yeah, I mean, which completely doesn't coincide. I'm not not sure. Yeah.
What if you had a bunch of quantities that had obeyed an algebra, including the Hamiltonian, that was more interesting than just commuting with Hamiltonian? If you had n quantities obeying some well-defined algebra,
Right.
that did not mean that did not necessarily be commuting with Hamiltonian. Would that be
But they have to commute. They don't even commute with each other.
not necessarily? They just
Yeah.
generate some interesting algebra, like Vera sort of kind of algebra.
Yeah. Well, I mean, I wouldn't call it Liouville integrable, but yeah.
you mean like that maybe template generally after that?
I'm thinking like in Vera sort of algebra, LNs don't commute with Hamiltonian. Yes. Their existence gives us a lot of power.
Like there's this notion of spectrum generating algebra or
Ah.
something, right? Where you move from one eigenvalue of the Hamiltonian to the other, so it doesn't commute through operators, but
But it
there's a
helps
nice
you
structure.
Right. Yeah. Okay.
Also, you shouldn't have discrete charges which are not part of this classification in the sense that there could be, the energy is a continuous variable.
Right.
And in a classical system, could you give a discrete sense of like some that would be outside of this.
Right. So in quantum, you can surely have classical. I mean, there may be. Yeah. Okay. So okay. I'll stick to this definition of integrability, and lax pair basically just a pair of L and M, which are two matrices, which are functions of these variables P and Q. And then the Hamiltonian can be written as L dot equal to ML. So if L dot equal to ML is equivalent to the Hamilton equations of motion, if there exists such a pair, then you say the system is integrable, because it immediately follows that trace of L power K is conserved. Okay?
Still in the classical setting?
Yeah. I'm complete. This whole talk is classical.
So by the commutator kind of thing, you mean what?
Poisson brackets. Yeah. Okay. So you can show that trace of sorry. Here M and L are matrices. Okay. Here M and L are matrices. Okay. So they are actually commutations, and if you take Ik dot here, then you can use this and show that Ik dot is conserved. Ik dot is 0. Okay.
So you have a classical phase space,
Mm-hmm.
and then you have a matrix which is defined as in terms of the observables P's and Q's.
Exactly. So you have L and M matrices which are defined with P and Q, such that L dot equal to ML is equivalent to your Hamilton equations of motion, and if such a pair exists, then you can show. Then it's obvious that trace of L power K is conserved. Hence, the system is integrable.
When you say n commutator L, should I understand that as the matrix commutator, and if there is a P commuting with the Q, that's the Poisson bracket?
So here is an example. Okay. So just for a single harmonic oscillator, L is just this, M is just this, and if you do L dot equal to ML, you will end up with these equations of motion.
But are P's and Q's their numbers, or
They are just numbers.
I think just matrix?
Just matrix commutation. Yeah. Just matrix. I mean, these matrices measure the size of the number of degrees of freedom. Okay. So if you take trace L power 1, it's just 0. So trace L square, if you do, you will get P square plus Q square. Okay. So this is just so you have lax pair, and then you have this n commuting integrals of motion. Okay. So I will show all these things for the Calogero model, where you have these big matrices, and L and M will be non-trivial, but L and M entries are just numbers. Okay.
What happened here was that there's 1 degree of freedom. We have to look at the matrix, but again, take L power 1 is 0.
Right.
So you got the right to come under 1.
Right.
So this is how it normally happens. You have to have a matrix with dimension on space, and then after space on 0,
Right, but you can if you use this and you put k anything, you can still generate other integrals of motion, but they'll all be, you can write them all in terms of your integrals of motion. I'll show you that example when I talk about Calogero model. Okay, yeah, so basically if you have n degrees, if you have n particles, then you generate n integrals of motion by taking trace of L power k. Okay, in principle L power k plus 3 is also conserved, but that will be some function of the integrals of motion, because any function of an integral is also is conserved, right? So
Can you just take the eigenvalue of
for what?
Can you take the eigenvalues of L as an inverse quantity?
No, I mean I'll show you that there are eigenvalues of matrices which actually happen to become positions of particles. Okay, so there's one more ingredient to this which I will explain, which makes the solving of the integrable model also easy. So till now we just showed that you can if you generate a Lax pair, then I know that the model is integrable. But question is, if I give you initial P's and Q's, how do you solve this dynamical system? And yeah.
So it must be that the collection of eigenvalues modulo permutation is one representation of the
Yes.
So the modulo permutation.
Well, except it seems that L is 2n by 2n. Is it 2n by 2n?
L is 2n by 2n, that's right, yeah.
And
Yeah, sorry.
I case is trace of L to the power k.
Yeah,
That k goes from 1 to n.
yeah,
Isn't it?
yeah, that k goes from 1.
There is some.
So here it went up to L square, right?
1 to
L was trivial.
L was trivial, no?
L was trivial. Trace L was trivial.
Trace L was 0.
No, I understand, but don't you have to go up to I to the 2n? You have to go up to trace L square for the case where n was 1.
Not,
Maybe n plus 1.
no,
So starting from 2.
Say you have a traceless matrix, you want to have no more than n independent.
yeah, you don't want, so if L power 1 is traceless, yeah, 2 to n, right, something like that. I mean, we will see that the question is, in this case L is traceless, but in Calogero model, let's check if L is traceless. So yeah. Then you just go one step more. Yeah.
So I
Yeah.
was under the impression that in general the size of the Lax pair matrix are not in a simple way related to the number of degrees of freedom for all elements. I thought that it's just some matrix. If you can find the matrix, then you are guaranteed that like trace n to the k is from k going from 1 to n, which is the independent one. And if you have any higher guys, those can always be written in terms of the first one.
Right. So
Wait, but if the matrix is too small, then you need 2 Q integrals.
Yeah, no, so obviously it's a bit
Larger than
We can also generate.
But I mean, what I'm saying is it's not a simple count like n plus 1 minus 2 n. For all integrals.
so the point is the size of L is 2n by 2n matrix, right? That at least for Calogero, Toda, I mean at least it may not be always the case, but at least for a large set of integrable models that I know it is the case. But that is one issue. Then the question is this power of k, how many of them you can take? That is another thing. So if you might have to go to higher powers of k to recover your n integrals of motion. Okay, so okay, so now you have this Lax pairs, and the question is now we'll go to some we'll go to an interesting example of a system of n particles on a straight line with x's and p's, and the thing is that this is just p square and this is 1 over xi minus xj square. Okay, this is your interaction, and this is a external trap. Okay, so the interesting thing is that this integrable model is also integrable in this kind of external potentials. Okay, so even if you break momentum conservation, you somehow have integrals of motion. So this is a very rare thing, that this a model in an external potential remains integrable, and Calogero family is sort of one prime example. and not only integrable for quadratic trap, but also it's shown to be integrable by Polychronakos innocence that it is integrable up to quartic potentials. So this is also for us interesting in terms of cold atomic experiments, because usually the trap is inevitable. So all cold atomic experiments which have interactions which might be integrable somehow actually break integrability because they have to trap the atoms. So it will be nice to have some model, at least a toy model, which remains integrable in presence of a trap. And the most common trap in cold atoms is a harmonic trap. So that is.
Since you bring that up, do you actually get this kind of potential in cold atoms?
So okay, so the sad thing is till now there is no realization of the Calogero-Sutherland gas. It's a bit sad because there are all sorts of Hamiltonians that are realized in cold atomic and ionic systems. There is one proposal few years back, a theoretical proposal of how you could think of generating a Calogero-Sutherland gas from maybe some dipolar gases in higher dimensions. But the proposal, I think, we believe is wrong. So even the proposal is not. So hopefully at some point, I mean, even if this is realized, it will be great if this kind of potential, yeah. So it's a long range interacting model with 1 over x square. Yes, yes. So you in the existing cold atomic, this thing, the most common Hamiltonian they have realized is something close to Liebnizer gas. There the interaction is contact interaction. So it's like a G delta xi exchange. Okay, okay. So they can also tune this. They can also tune the contact interactions. So our hope is that so most of the cold atomic experiments, apart from some recent experiments apart from experiments in dipolar gases and so on, most of them are contact-like interactions. But as I will show, the Calogero family has some very short-range interactions generalizations. So our guess is, I mean, we also showed that many properties remain common between Calogero and the existing cold atomic gases. So I will. Yeah, so I'm talking about experiments in which you have so many atoms that you sort of have some sort of a collective phenomena where you can describe it by a mean field theory with contact-like interactions. I mean, basically, yeah. Okay, so from here you can write the equations of motion, which is this. Okay, so now the question is, what are the Lax pairs for this Calogero model, and can I in general generate a series of Calogero models using Lax pair formalism? So this is okay. So this is just please remember this potential, and we'll come back to this again. So the sort of more systematic way of generating Lax pair for the Calogero family is just assume a Hamiltonian of this form. So we'll discuss the case without potentials. Okay, no external potential. Okay, only two body terms, only terms like this. Okay. So we start with a Hamiltonian with a general form of V. Okay. Now where V has this symmetry condition because you want them to depend only on xi minus xj. Okay, the distance. So now you start with an ansatz. Okay, this is an ansatz of L and M, those L and M matrices. Okay. So just to answer somebody's question, if you see trace of L here, it is just sum of P. Okay, so sum of P is sort of trivially conserved. Okay, so you have to go for one additional thing to generate. Okay, so start with L and M, but with very general conditions. That is just. So how does this L and M look? L looks like your P's on the diagonal, and on the off diagonal you have some coupling constant times some function of Qi minus Qj. Okay?
That x there is just a
function, any function. Okay, any function. The off diagonal terms, no, can be imaginary. Yeah. I'm not specified what is z's and y's. Yeah, it's also imaginary. Sorry. Yeah. It's also imaginary. Okay. So these are just functions, chi, z, and y. Okay. So now the question is, now if you make sure that L dot equal to IML, okay, and if you make sure that that is equivalent to the Hamilton equations, then you get some functional equations in terms of chi's and z's and so on. Okay. And these are called sometimes they are called addition theorems and so on. So what kind of functions satisfy these equations? Okay. And it turns out that these are the functions that satisfy these kind of addition theorems. So just by starting with it's just the most general Hamiltonian, making some ansatz for the Lax pair, and solving these addition functional equations, you can generate all the forms of chi. XY? Yeah.
You are insisting that the Lax pair equation reduces to the Hamiltonian.
Yes, yes.
So that you are assuming some.
Yeah, so basically you are getting some relation between chi's and z's and v's, v of, so zeta here is qi minus qj, okay, zeta is qi minus qj. So v turns out to be chi of zeta square plus a constant, okay, chi is here, x, okay, what is x, okay, x of zeta plus a constant. So quickly we'll recover all our if x of zeta is 1 over zeta, then this v is 1 over zeta square. That is my rational Calogero model. If it is 1 over sinh, then it is 1 over sinh square. That is my hyperbolic Calogero model. So 1 over sinh square is very short range interaction. Okay. So this is probably the closest favorite of the cold atomic systems, because this is 1 over sin square, so it quickly goes down, and 1 over sine square, and then this square, which is the Weierstrass P function. Okay. Yeah. Is there a question? Okay.
Did either HRI or ICTS have a question?
Okay.
So have you found the most general integrable system with a Hamiltonian or this form of this?
No.
This is a full set of
This. So the thing is that if you start with this, and no, it's not necessary. So the question you are asking whether this is yeah, I'm not sure if this is a unique solution. So yeah.
So where did you put in something extra? So you put in the Hamiltonian.
Yeah.
And then everything seems to follow, right?
Yeah. So you put in the Hamiltonian, write your Hamilton equations of motion. Okay. Then you make this ansatz for L and M and write L dot equal to ML. Just see the previous thing. Let me show you the previous. Okay. I don't have this. So if I know L and M for the Calogero model and do L dot equal to ML, and I compare element by element, I should get these equations. You will quickly see it in the I'll then okay. So where is y? Yeah. So
Maybe y is also fixed.
no, y gets fixed. Y gets fixed. So yeah. There's one more equation. Yeah, you will get a bunch of conditions. This is I gave you one example that needs to be solved. Yeah, that is true. Sorry. Yeah.
I'm sorry for being so, but is that 1 over sine hyperbolic or is it sine hyperbolic inverse?
This is 1 over sine hyperbolic. Yeah.
Just trying to figure out. And what was the connection to the Weierstrass function?
Yeah. So it's the thing is that, so let me just my next slide has the answer to that.
Okay.
So
Yes, I and J run from 1 to n.
I and J run from 1 to n. Yeah.
So in this case, it's an n cross n. These are n cross n.
These are n cross n matrices. That's correct. That's correct. Yeah. Right.
In the other case, trace was 0. Here it's not trace.
No, here trace of L is sum of all P.
Momentum conservation. But that's a non-trivial conservation.
Right. So yeah, that's true. So
It does suggest that you might have a broader answer and discover larger classes.
yes, yes. So we made, so I'll come to that. So in the later part of my talk, where we made a slightly broader ansatz, and we ended up getting all these different forms. Yeah, but things are not clear. I'll just come to.
How did you come by that?
How do- yeah. No, that's okay. First of all, this is the older work. So this we didn't come up with. Okay. So okay. Secondly, yeah, to my knowledge, there is it's an ansatz. There is no. I mean, no. I mean there is a. Yeah, I'm not aware of a systematic way to make that ansatz. At least I am not sure. And
I mean, like, look at your equation. B is equal to x squared. It seems that you give this first, and you find out, okay, there is a B.
Yeah.
For which it happens.
so one thing is that I mean, okay, just to
L and N have to be clever. Yeah.
so in the rational case, which is 1 over r square, one could try to make L and M just for the rational case, and from that try to generalize, because L and M for the rational case has this form very intuitively. So maybe that is the way, but I don't know how. I mean, it could just be that these guys just wrote something and worked. I mean,
But if you write, something and you get some other equation,
Huh.
Which is not a canonical equation,
Huh.
like that also is some integrable system, right? in this order.
but you should be able to solve for this functional equation. No? So
You will get a different set of functions.
no, but there is no guarantee that there is solutions for the functional equation. So if there exist solutions for the functional equation, then even if you don't know the solutions, if you prove that there exist for solutions, then you can say that there is some integrable model. Yeah.
The integrable is a solution to the analog of these, the complete set of equations.
Yeah.
Just I make one comment. Like, there are multiple approaches to it. Like, I don't know, one of them is, of course, Maxwell model, but there are also like inverse scattering methods and so on. So in inverse scattering, you would actually go about trying to find a potential
Yes.
that has a particular, the solutions have a particular behavior.
Yes. Yes.
So if you say you have particular behavior for your solution,
Yeah.
you can do two things. Then you can use inverse scattering to construct.
Yeah.
Or reconstruct the behavior.
But the problem is, even if you know that, even if you are able to guess this 1 over psi square systematically, to regenerate the lattice pair is still a complicated problem. If I tell you this is a solution, so yeah. Okay, so the answer to Sandeep's question. Right. So the question is, so we have 1 over r square, 1 over sine square, 1 over sin square, and the elliptic function. So let me show you that. So how does 1 over sine square come about? 1 over sine square just comes about by taking 1 over r square and making it periodic on the real axis. Okay, so just put x plus nl and sum over all n, and you will get 1 over sine square. Coincidentally, it is just the chord distance on a circle. That's a coincidence. Okay. Now it also turns out that even this, in addition to these external potentials, is integrable. But I'll come. I mean, this is not crucial at the moment. 1 over sin square comes if you make it periodic on the imaginary axis. Okay, you will get sinh. Now, if you make it periodic on both, then you will get the Weierstrass P function. Okay, so you get Weierstrass. So, and the square of those Jacobi functions, there are some identities which is basically Weierstrass function. So, don't know. Yeah. Actually, I don't know sin square also, because sin square sort of I have. I mean, sin square, you can just think of it as on a line, and they are just right. So. Yeah. Yeah, sure. You can go to this, you can go to this, you can go to rational case, all from Weierstrass function. Okay, so Weierstrass is the most general case.
So what you're saying is that Coulomb gas in one line is integrable.
No, that's not. That's one. We are talking 1 over r square potential. Yeah, and the force is 1 over r cube. Here. So. Yeah, at most you can think of dipolar gas, and you just do one integration and get 1 over r square from 1 over r cube. But there are some vague proposal. But
Dipolar, I mean, it seems important that when they come very close, it is 1 over x square. I don't know. Is that important? And that seems to be the crucial thing.
that's right. That's right.
When they're very close, it's
Yes.
more singular.
Yeah. Yeah.
All three potential factors.
Yeah. Okay, so let me. So why are we interested in this Calogero family of models? I'll just flash 2 slides very quickly. One is it also comes in contact with something called Benjamin-Ono equation, which is a fluid equation for stratified fluids. This is just a non-local partial differential equation. It's fairly simple looking, but this is itself integrable. Okay, but then the Benjamin-Ono has solutions of this form whose poles are Calogero particles. Okay, so this is one interesting thing, that the soliton solutions of Benjamin-Ono equation, the centers of them are like Calogero particles. Okay, so there is some and I'll talk about nonlinear dynamics, and also we are interested in context of shock waves and so on and so forth in these integrable models. So the question, yeah.
Physically speaking, how does the dynamics become non-local?
Which dynamics?
Dynamics which is where, how does it become non-local?
This one. This is a solution of this equation.
Yeah, that equation.
Yeah.
Physically, how is it becoming? How is it become non-local?
You mean the Benjamin-Ono equation itself? Well, so the derivation of Benjamin-Ono like equations for fluids, I mean, it's a very detailed thing. So it's
Roughly, how does it become? How does the parallel side affect something that is going on here?
yeah. So I mean, okay. So
Is it very important that you are this type of setting?
is this type of setting? It's actually not.
Isn't the equation itself non-local? The differential equation itself is non-local, isn't it?
Yeah, that's what I'm asking.
Yeah,
I think where that
he's asking the origin of that.
what physical system
Mm.
is that?
Yeah,
Where does it come about, the non-locality?
yeah,
What does it model? You're asking what?
yeah.
Not model, but where does it come from? How systematic is it? Is it generally that you would expect some of the
Supposed to be the height of the interface.
Yeah, U is supposed to be the height of the interface. Okay, so
But just to understand Abhijit's question, as far as I understand, he just defined an equation.
He's also saying that this is the equation that
For
covers
something.
yeah, yeah, yeah. So
asking how does this dynamics become non-local?
yeah, it's I mean, it's okay. One thing I can say is that it need not be stratified. There are some very different regimes in fluids. If it's a shallow water wave, then it's a KdV equation. But apart from that, I mean, yeah,
Sorry for being so element. It means that you have a sudden
yeah,
change in
sudden
density.
change. Yeah. Yeah. No. So Calogero model for large number of particles has its own field theory description. Okay. What I'm saying is that the Benjamin-Ono equation, this is a non-local PDE. It turns out to be integrable on its own. Okay. Because it is integrable, it has multi-soliton solutions. Okay. Because if a model has multi-soliton solutions, then the model is integrable. That's another thing. Yeah, if you have 1 or 2 soliton solutions, it is not integrable. But if you have 3 or more, it is considered integrable. Okay, because it has multi-soliton solutions, the centers of these solitons, okay, they behave like Calogero particles. So take this equation, plug it here, and write equation of motion for A dot, A double dot. A double dot satisfies Calogero model. Okay?
But I think Kedar asked this for initial answer. U is the local velocity of this system?
U is the height.
U is the height.
Height, yeah.
Because there's also a velocity, so maybe it's somehow integrating that also.
Yeah, I mean the exact 1 over x minus y. Yeah. Okay, so
Since you
Yeah.
said all this, the poles, the height kind of diverges there. Is it somehow a
Uh,
similar? U is the height, right?
U is the height.
So if x equals A of j, at that location the height blows up.
No, here A is complex, and it has it behaves like Calogero particles.
So physically you never hit the pole.
Physically, yeah,
This is valued at real x, but the poles all lie complex.
complex. Right.
What they do the Calogero particles are real.
Yeah, but you can make them complex. Yeah, and even if you make them complex, they remain integrable. Yeah. 1 over r square.
And even if that was real, the two poles cancel.
Oh yeah,
So,
right.
but okay.
Yeah.
I was wondering whether, I was confused about
Right.
He seemed to indicate they were imaginary, sorry.
Yeah, no, but the point is they can come to the real axis, right? They can start, they can be imaginary, but in time they can evolve and hit the real. Here.
Then they can.
Yeah.
Okay, sorry.
So this is, if you take A is equal to, okay, let me not, I'll do that later. So okay. So several features of Calogero are already similar to short range cold atomic systems. We showed some properties long ago. In some sense it is understandable because even 1 over r square is 1 over r cube in force. That is much faster than 1 over r power d. So even the power law is sort of short ranged. But if you, I mean, so it can have short range properties, but that's very heuristic. So, okay, so this is just a collection of references where Calogero models appear. So it is just for literature purposes. I have been interested in just a few, I worked on just a few aspects of this, solitons, quenchers, and duality and so on, and I'll talk about that. And okay, so now the question is, how do we solve this integral model? So question is, if I give you initial pi's of 0 and qi's of 0, how do I find pi of t and qi of t without doing actually Newton's laws?
So fractional statistics meaning you quantize the system and then
Yeah. Many of them are for quantum case, but this is just collection. Quantum theory is also integrable. Quantum theory is also integrable in a trap. So that is yeah. Okay. So now integration of the Calogero model by something called projection method. So now the idea is, I have p's and q's, and I want to evolve it, and I want to find pi of t and qi of t. Okay. And then I'm going to talk about soliton solutions and so on. Then I'm going to define soliton solutions. So my aim is just to solve an initial value problem. So it turns out that that if you assume that there is a large n by n Hermitian matrix with 0 trace, just then the Hermitian matrix evolves as AT plus B. This is just take a Hermitian matrix and just evolves as AT plus B. Okay. You can show that if there exists a lax pair, then the solutions of equations of motion can be written as AT plus B. Okay, so this is a very powerful trick that I don't want to evolve p's and q's by Newton equations. These are like long range. Every particle is interacting with every other particle, and it's harder. It's doable definitely, but it's harder. The question is, can I do it exactly? Okay, so the only thing you need to do is you define your lax pair at t equal to 0, okay, and that I call it as L of 0. What is my lax pair at t equal to 0? My lax pair at t equal to 0 is p1 of 0, pn of 0, and I believe there was something like ij x1 of 0 minus x2 of 0 and some. So you make a lax matrix from the initial condition. Then make a lax matrix for your q of 0, and q of 0 is just x1 of 0 up to xn of 0.
I forgot what Q was.
Yes, q is just a position. Where is? Yeah, q is there. Okay. I'm sorry if I moved from x and q at some point, but okay. So then the solution. Then if I do q of 0 plus L of 0 t, I have a new matrix. And the eigenvalues of this matrix are my Calogero particles. Are the new positions. Are the new positions. Okay. So this is for us. Yeah. So the underlying sketch is here. So the point is x is at plus b, and then you can diagonalize q. X of 0 is traceless. Yeah. Okay. Then you can diagonalize q, or you can diagonalize x like this. Okay. And then if you take our derivative, you will get something like this with lax matrices. Okay. And then you can show that the solutions are this. Okay.
Q is the diagonal this thing, but it's also, I mean, these are positions you're saying, but you're also saying that there is the eigenvalues of the x.
Eigenvalues of x at any time t are the positions of particles at time t.
That was somehow.
Yeah, because
So this
yeah.
is the same as your x, y, z thing, right?
This x is no. This x is just a n by n Hermitian matrix. Okay. So maybe okay. So so you have a 0 trace, and start with any Hermitian matrix, and define x is, and the solution is at plus b.
That's by definition.
That's by definition. Okay. Then call the diagonalizing x at any time gives you the diagonal elements q.
So that's the definition of the relationship between Q and X.
That's the definition of the relation with q and x. Okay. Then you know that right.
Then you use the equation of motion for Q.
Then you use the equation motion of no. Then you one second. So yeah. So then take this and take a derivative with respect to time. Okay. On the right hand side you have a. Okay. On the left hand side you have x dot. Take dot of this. Then you will produce a bunch of things. Dot of u's, dot of q's, and all. You will get exactly this
By using the equation of motion of Q in terms of the lax.
by using equation motion of q in terms of lax.
So somehow equation of motion of Q tells you that.
Yeah. Okay. Okay. So yeah. Okay.
Very powerful. You say all you do is
Yeah.
figure out what Q0 and L0 are, and
Yeah.
then you know at all times.
At all times. So
very practical way of solving the problem.
yeah.
Yeah.
Is it, and the reason this is very important for us is that when you want to study things like what happens long-term behavior after a quench, or soliton solutions, you don't want to do Newtonian dynamics, because even if you accumulate small errors, you cannot really rigorously test whether it's a soliton. Here there are no errors. There's no iteration in time. At any time I know where the particles are.
Yeah, it's clearly that, I mean, just written down the solution.
Yeah, that's it. So it's very so yeah. So that is the thing. Okay. So then
I'm sorry, it seems too much to plan. I mean, so you have your q dot equal to p. Okay, so you have this diagonal matrix which is called q p, and you have q dot equal to p fine. So, but where is the p dot equation? Where is the you are using so p dot equal to q is just definition, right? So,
q dot equal to p is the definition. Yeah.
So p dot,
Mhm.
which will have the dynamics. Where are you using that?
So where does L come in?
Yeah.
So L is so take dot here, L dot. Okay. then you get P dot plus some stuff here, okay, and then
I think
yeah,
proving that L dot plus I n comma L is 0,
yeah,
you use the
right,
properties of the.
right, right, right.
So, but where is the hard labor? I mean, in order to find u as a function of the potential of the system, or where is the potential going in?
Potential is going into L0 and Q0.
That's the initial condition.
Right, but that has the information of the potential, no?
Where, how? The form of it.
See,
The form of L.
L is connected with these functions which appear then sort of in, like it has 1 over xi, whereas the potential is 1 over xi squared.
Right. That was the definition of equation of motion, right? No, no, we know that there exists a Lax pair for the Calogero model. Now, if there exists a Lax pair, then the solution is of this form. That's what we are saying. But maybe
I mean, from one kind of potential to another kind of potential, where will the change be?
in L and yeah, in L.
But L is even plus I so in will so little u will is it?
No, L and M both will change if you change the potential.
In the end, you don't care about u. If you knew what the form of L was, he had L and M in the previous thing in terms of functions of P and Q. So just use that. You change the potential, the form of L as a function of P and Q. But apparently Q is just this diagonal
Right.
matrix with just Q.
Right.
Q is universal. L is not. Like for instance, here had some information.
When you first introduced L, it was in terms of a commutator of two things, right? The Lax pair.
The Lax pair was L and M.
Sorry, when you first introduced it, what was the connection between L and M?
The connection was that L dot equal to L dot L dot equal to LM or ML, L dot plus ML equals 0. That is the equations of motion.
So you should have such a pair.
If you have such a pair,
Good.
then
Okay,
yeah,
Good. Got
yeah.
it.
Oh, I see. So if you have already invented what
that's
is,
right.
Yes, yes.
then you go on
Yeah.
Right,
find
right.
what Q and P.
Right, 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 right. That's right, but right. I don't know if it's always the case again.
Specific to the Calogero
Um,
projection. I mean, also other questions.
No, no. This is actually not specific to the Calogero model. This is you can do this for TODA also. You can do
Any Lax system.
for any Lax system. Yeah, yeah.
So what seems better along those lines is that the thing that moves linearly in time is the original position. I mean, normally the angular variables are very complicated functions
Right.
of the original theta. Here it's the Q itself that's moving linearly in time.
Right, right,
So it's a very special system.
right. But at any point of time, the resulting matrix is not diagonal. That is a very complicated matrix.
What?
At any point of time,
Huh?
the resulting matrix X is not diagonal.
So which is the position? Q or?
Q is the position.
So this thing, when I do this,
Yeah.
oh I see. So this is you get a matrix and then you have to diagonalize it.
Exactly.
Oh,
Exactly.
so
Exactly. Yeah, yeah, yeah.
You keep diagonalizing.
Yeah.
I understand.
Yeah, yeah.
So the eigenvalues of this are the position. So the matrices are the angle variables. No, but there are n squared. Anyway, no. The eigenvalues, the things that are linear in time are linear. So it's not clear that the eigenvalues of the
Yeah.
the matrix elements themselves.
Yeah.
So there are n squared of them, but there should be only n angle variables. So somehow they all depend.
But the metric works presumably anytime you relax it,
Yes, yes, yes. Right, right. Yeah, I don't.
Does it even need n integrable? I guess it needs n integrable.
But if you have a lax pair, then you have n integrals of motion. If you don't have a if it's not integrable, you will not get a lax pair. So, yeah. So the reason it's called projection method is the idea is that you have these particles which have very complicated interaction, but you go one dimension higher into matrices, but the matrix evolves trivially, and then you project the matrices by calculating its eigenvalues, and the eigenvalues are complicated. So that's the only, yeah. Yeah, so everything goes into LNM. Next slide is the example. Yeah.
So you say the eigenvalues of these are positions of the particles. Let's say Q0 is 0, starting from the origin. Now
No, 1 second. Q0 is everything from the origin. You have n particles, right?
Yeah.
So you have to arrange them.
Especially potential
Blows up. So
Yeah, I thought the initial point was not that important, but let's say, because Q0 is anyway diagonal matrix, so diagonalization that I have to do is kind of at L0 and
yeah.
now the trace of L to some power k is also integral of motion.
Trace of L per k.
That's the standard conception of
Right.
integrals of motion.
Right.
And now you're saying the eigenvalues of L are essentially position dependent, time dependent positions.
Eigenvalues of X, time dependent
So
position.
now if I take the trace of L to the power k, it just trace sum of k power of positions.
No, because see, you have to take L matrix, okay, which will be function of positions and momentum at any time. So you take L power t, take trace of L power t power k. Okay, this is different. Okay, so let me go to the example. So this is an example of L and M matrices, but now we are talking about the harmonic trap. So everything sort of goes through with only difference that you have omega square q here. Okay, so this is the equivalence. So take this equations, put it here, you will get this equations. Okay, and this basically what it says is that
it's still a lax pair system.
yeah, with this extra term. But just to answer Sandeep's question, what is integrable is now trace of L plus L minus. So it's slightly. So yeah.
How is trace of L?
So it will be L plus L minus power k. Okay, this is what is integrable. So this is basically IK. So there's some it gets generalized a little bit, but the idea is that you will end up getting matrices which now are in a harmonic trap. But that is simple. You just write down the solution. Okay, Q0 cos omega t plus, and that's it. Take the eigenvalues, and those are the.
Are these Q matrices, are they Hermitian?
Q matrices are just positions of particles.
The thing that you had to diagonalize in order to get the position.
Those are Hermitian. Those are Hermitian.
So for instance, there was 2 cross 2. It's like you've got motion on the group manifold. Like it's like on a sphere. It's like apart from the trace part. You're moving on a sphere, and the thing that is physical is the under the weighting of force.
Okay. Yeah.
Totally irrelevant, but just from your harmonic oscillator case, where you needed a bigger matrix, in that case, it might be that you can recast this as a standard lax system without L plus and L minus, but with a bigger. Anyway.
Okay.
P minus.
Yeah.
Anyway,
That
irrelevant. Go on.
that my yeah. So it's
It's interesting to generalize.
so. Okay, so this is the. So this is the solution. Yeah.
Is this called projection method because it's a linear motion of this big space and then it projects down to the algebra?
Exactly. That is the reason. It's just that if you go one dimension higher, it is very trivial, and then you.
In the matrix space, it's just a linear motion.
Yeah.
You have to project down to the algebra.
Yeah.
And that projection gives you all the numbers.
And it's either linear or it's something like this. X double dot is minus omega square.
Because you still haven't done the whole thing. I mean, even here, once you have got the harmonic
Yeah.
Clearly there is an angle which is going linearly.
Right.
This is a further transformation from x to something else.
That's right. That's right.
You know,
Yeah.
because x is this is a cosine. I mean, this is a harmonic thing.
Right. Right.
So presumably there is some other transformation which goes all the way to linear.
Exactly. I think that's what maybe Sandeep is also saying. Maybe there is a way to extend the size of the lax matrices so that you don't write it in this form, but write it in the form that I originally said, something like that. So.
Harmonic oscillator, in that case, the form is a little different, so I'm just saying that generalized.
What's the problem?
Okay. So. Okay. So now coming to the quadratic case. So I heard that time is not an issue. So
1:30. My request is 1:30. Others might want to go.
Okay. Okay. So I'll yeah. So this is again the Hamilton. So now I'm going to discuss the notion of solitons for this finite dimensional case and so on. So before that, let's rewrite the Hamiltonian like this. So you can rewrite the Hamiltonian in this positive definite form, and then the background solutions. So what do we have now? We have n particles in a harmonic trap, plus they have this 1/r² repulsion. So they cannot come too close, but they cannot go too far. Okay. So question is, how do they arrange themselves? Okay. So the background solution is when all pj's are 0. So all momentums are 0, and xj's satisfy this.
Meaning the lowest energy configuration.
Lowest energy configuration is such that pj's are all 0 and xj's satisfy this.
This is minimizing the potential.
Minimizing the potential. So this is called the Stieltjes problem, and the solutions of this turn out to be zeroth of nth Hermite polynomials. So you take if you have 10 particles, write down the 10th Hermite polynomial, find its zeros, and that is where the Calogero particles sit for minimum energy.
So if you take n to infinity, you get a nice.
Yes, I'll come to that. That is in fact that is probably after lunch. So yeah, so I'll come to that. Okay, so so that is the thing. There are zeros of the nth Hermite polynomial.
Why does it happen? I mean, it would, you know, if you told me, if I take a Slater determinant of Hermite polynomial, then it becomes like a Fermi sea, and so on and so forth, and then, you know, I mean, I don't know what.
Yeah. So okay, there is. I mean, then okay. I think you can show, knowing that it is zeros of the Hermite polynomial, there is some proof to show that those are Calogero particles, but yeah, if yeah, so that's anyway. So now the question is, what do I call solitons?
So let me understand. How the nth zero scales like what power of n? So am I correct?
At large n it's like this. So the n minus 1th 0 and nth 0, they go as something like this.
So this is the location of the last zero. I want to see how far off the trap you're going.
Oh, the location of the last 0 is
Some positive power, right?
yeah. So yeah, I have it in the very last slide. So
It's okay.
yeah. So the yeah. So I got yeah. So your the thing is, it I think it goes as n. It goes as n. Yeah. The nth 0 is at n. Yeah. With some corrections of this form. With the gamma, where gamma are zeros of the Airy function. So something like that. Something like that.
And if you have n fermions in a harmonic trap,
Yeah.
the nth fermion will be like square root.
Yes. Yes.
So this is even more repulsive than fermion.
Oh.
It's further away from each other.
Sorry. One second. So is it?
Because x square root.
Right. So maybe we'll come to this when we talk about the continuum limits. So I I can tell you how the, so let me just tell you how the rho of x looks. Rho of x at n going to infinity limit goes as r square minus x square, and r goes as n. Yeah. Okay, I am not.
With size x. With size x. And r goes like n.
Yeah.
So then x goes like
N.
n.
The last guy goes to N. If you push quite far.
And here also it would seem that x should go like n, right? The zero. I mean, if you had an nth order polynomial with order 1 coefficients,
Yeah.
the nth zero, which is sort of balancing all, should go
Should
like
go,
n.
right. Okay, but I'll talk about the continuum limit soon.
Yeah.
So what is so what we call solitons are the following. So in continuum cases, in like PDEs and differential equations, we can define soliton solutions as some special solution of rho of x comma t, such that this rho of x comma t is a function of rho and just a function of few of these. Okay, this is the definition. So so one example is this: if rho of x comma t is rho is a function of x minus zt. Okay, so it's a simple function of z, but z has some simple evolution. Yeah, this is for larger. I'm just defining. Then I'll talk about my case, finite dimensional case. Okay. So if you have say some hydrodynamic theory, and you want to define soliton solutions, what you say is, you say I will substitute rho of x minus vt and v of x minus vt, this is soliton velocity, into my hydrodynamic equations of motion, and then it will satisfy. It is very non-trivial to find this, because the hydrodynamic will be nonlinear hydrodynamic theories. Okay, so there has to be balance of all these terms such that this satisfies the equations of motion. Meaning that this is a case where rho is a function of x minus z, where z is nothing but vt. Okay, which means that it's a function of some few parameters, z1, z2, z3, such that z has very simple evolution. Here z double dot is 0. Okay, so that is for the Calogero case with no potential, just interaction without harmonic potential, the soliton solutions are Lorentzian. That was shown by Polychronakos long ago, and that's just x minus vt whole square plus b square. Exactly. So solitons are essentially finite dimensional reductions of an infinite dimensional space. No harmonic trap, no external potential. Okay, no external potential. No external potential. Okay, so no external potential. The soliton solutions are Lorentzian. That was shown. So if you make a Lorentzian ansatz and put it in your equations, in your equation for the continuum theory, they will satisfy those equations. Okay, so this is the form of the solution. No, take rho of x comma t. So it's a. No. There are some constraints on A and B. Very particular constraints on A and B. But there exists Lorentzian. If you take KdV, then you have some secant hyperbolic solutions. So it depends on which integrable model, you have different solutions. For this, Lorentzian is a solution, and this is a soliton, and you see it just moves with some speed v. So it's a robust solution of your theory.
Are there also multi-soliton solutions?
Yeah. So you have to have multi-soliton solutions. If the model is integrable, usually, I mean, you need to show that there are multi-soliton solutions. So there will be several z's, okay, which will be of each of which may have their own trivial form, but they will have some functional dependence like this.
Which comes in intuitive to me for the 1 over x square potential, that the density peaks together and I might have thought that the particles like to spread out a bit.
No, so the point is, it's not actually just the densities. If you think of the discrete system, it's like very special initial conditions, right? Is some positions and velocity, and somehow that shape will remain, right? I will show you such a configuration. Yeah. Okay, so is this, so basically I am just trying to say that you have special solutions of your general rho of x comma t which are parameterized by few z's, and these z's have some simple evolution. Now the question is, how do I define for finite number of particles? So our definition is the following, that my job is to give pi's and qi's. Okay, once I give pi's and q's, everything is determined. Question is, how am I going to choose the space of initial conditions? Okay, so for us, solitons are essentially finely tuned initial conditions. They essentially restrict the space of initial conditions. So I cannot start with any initial condition, it will just break. As Sandeep was saying, I mean, if you have, like, you just create a lump of particles and give them initial velocity 0, essentially they will break. Okay, so your positions and velocities should be so fine tuned that they will all move in a synchronous manner forever. Okay, so they basically restrict the space of initial conditions. So basically I need some dual variable z which I will use to choose my initial conditions. Once I choose my initial conditions, I am done. I will disregard z. Z may evolve, I will show how z evolves. Okay, so the above initial conditions are obtained by specifying few parameters. For example, if there is one soliton, there is only one z. And the dual variable z follow their own independent evolution. In Calogero, what happens is the z's also behave like Calogero particles. Okay, okay. So that is the thing. So z's also behave like. So if you have a single z, then z double dot is minus omega square z. You have only single z. But if you have z1, z2, okay, if you have z1, z2, then you can imagine what you get. Z1 dot is equal to, Z1 double dot is minus omega square z1 plus 1 over z1 minus z2 whole cube or something. Okay, so just two, if you have two soliton solution, the z's will behave like Calogero particles. Yeah.
No, now by the time you have n soliton solutions, you have as many initial conditions.
Absolutely, absolutely.
So then the initial condition is not finely tuned.
Exactly. The more z you have access to, you have yeah, and if you have z as much as n, then you are yeah. So essentially it's like, yeah, so that's the
Statement that dual z has their own independent evolution is true for some small number of solitons compared to n.
no. You for even for n 300 you can have one z solution. I'll show you.
Yeah. What I'm saying is that if you increase the number of solitons, it becomes comparable to the number of particles. You just lost distinction between.
Yeah, but no, but still, yeah, for z equal to n, yeah, but you still have the notion of many solitons moving and yeah. Yeah.
Sticking to a particular lower dimensional substrate, solitons do not like to be applied to a slower dimensional. So when you have the number of z's of order like number of basic directions, you basically can't restrict to the substrate everywhere. Is that what you're saying? Maybe they will still show that those z's also follow.
If you've got n z,
Huh.
so you've got the same solution there. Now if you do the solitons of that new the system of z, you get back to the original system. Is it like a z cube here?
I think so. So if you have n, so we were trying to do something like this. So treat the nz's itself as a whole Calogero system,
Yeah.
and find solitons of that.
And you get back to the original variable?
Yeah. If I need some time to, we are actually trying to think about that. Yeah. So the, okay. So.
But this suggests, if that's the case, this suggests that the quantum system based on this has a very interesting duality. Right?
Yeah, that is so that.
Yeah.
Yeah. So yeah.
So far, just to be clear, you just told us, okay, the continuum,
Hmm.
and then that's where you take n going to infinity first,
Hmm.
I would say. And then, but then you say for a finite number,
Yeah.
now there, what is the analog of saying that rho has to have a certain form? It's just that there is some way
Right.
in terms of some other parameters.
Right. So actually, right. So actually, the reason I just put this is just because we are more used to continuum thing.
That's the idea what that is.
But if you take the finite number and then take the n going to infinity limit for Calogero, you will slowly hit.
But otherwise, you're going to tell us how you define the finite parameter.
Yeah. No, that is the, that is, So question is now, so this is, so let me start with x's and z's. And here in x's and z's, nothing is necessarily real. It can all be complex. Okay, x's and z's can be complex. And if I take one more derivative here, okay, then it turns out that x's and z's completely decouple. Okay, so
This does suggest that it's very much like a S duality, because if you look at the role Z plays in X in the role, it's
hmm.
One might especially because the Calogero model the right on the spectrum curve, Calogero model converges to the same as the spectrum curve of the hyperbolic equation. So in Phys they have as well. So one might do this.
Really?
Not quite clear what exactly, what are the X's? X's I'm not sure, but if you say that trace as the case, it will correspond to the direction of the meromorphic. So that may be a better language to describe the S-duality. So the S-duality is the Coulomb direction would be like we take the trace phi to the phi with the S-line together.
no, that I know.
In here, that those would correspond to the I case, that trace sensitivity.
Trace sensitivity. So
No, I mean, but you have to specify where you're sitting in the two.
oh, one for choice of action.
So those might be related to the trace sensitivity case. Maybe
So in the later part of my talk, we start.
That they will essentially clarify the integrated structure of the Coulomb branch, but once you reduce to 3D, you will also get this limit on top of it, and then they together explain that the integrated structure on that essentially is the Calogero equation.
Okay, so I mean, yeah, I'll describe some method using prepotentials where we get these dualities, but that's later part of my talk. So basically this is this. This is actually quite a non-trivial lengthy exercise. It's not really obvious. We have to use many identities, and the important thing is that it works for m less than n. So that is the most important thing. The fact that it works for m less than n. So and as soon as I specify my m, it even works for m equal to 1. Okay. So if I put m equal to 1, then still I will get these.
Less than equal to n?
M less than equal to n, yeah.
So m equal to n is the most important. That's the real one.
Yes, yeah, but we want soliton solutions, so we are yeah. Okay. So here right. So then here see this minus I and plus I. No, what I'm saying is that the fact that you take one more derivative and you get this decoupled equation somehow holds for m less than n. Okay, it was okay. So the m soliton solution. So here I guess we can just impose reality conditions on x's, and then by equating real and imaginary parts you get this. So that means my one soliton solution is given by this equation. Okay, so my single z, okay, you give me a z, so let's say put z equal to 3i, okay, and then I will just calculate all p's and x's, p's of 0 and x of 0. For that we can do some, for that you need to do a little bit of numerics because you have to do some viscous equation, but you just I have to find the solutions for a given z. Okay. So if z is infinity, then it was the usual Stieltjes problem. So these are the Hermite polynomials. Okay. So what is happening is that you take all z's to infinity, then you are sitting on zeros of Hermite polynomial. Bring one z slowly. Okay. And bring one z slowly. All the p's and q's arrange themselves. Okay. And then let it evolve, and that will be like a soliton solution. Okay. And the z itself will do this trivial evolution. It will go around an ellipse.
Sorry, please, I will just so you start with the ground state with n minus 1 particle.
With n particles.
With n particles. And then what?
And then you have a z far away.
Z meaning your soliton.
Your soliton parameter. Okay. So if it's far away, then this term is not there at all. Okay. And then these are basically at zeros of your Hermite polynomial. Okay. Then you bring your z close to those particles. This z acts like an attractor. So these particles will get attracted. Not only they'll get attracted, their velocities also will be now adjusted. And you'll create a very special pi's at t equal to 0 and qi's at t equal to 0.
You're telling us what initial conditions
To start with. And yeah, what initial condition, and to do that I need a z. And then once I have this, I use my projection method and evolve it. Okay. So and z motion of z itself, I think is okay. It goes on ellipse, but there are some interesting things I'll show you in the next 2 slides.
And the two soliton solution, you just have
Two of these.
Yeah.
So this is the m soliton solution.
Yeah.
Okay, you have 2 of this, but the motion of z will be slightly non-trivial now.
Fine.
They will be Calogero. Okay. Z1 and Z1 bar.
He means that this Z usually satisfies Z1 double dot to PC.
No, but I mean,
the position of the dot.
Yeah. No, I think he's saying that when you consider instant, it has a modulus, right? But here there is no such thing. It's a soliton.
Just the location.
just location of the center of the soliton.
This Z1 is a soliton coordinate.
Yeah, Z1 is the soliton.
The soliton itself is in a harmonic oscillator.
In this case, because there is only one Z1. So one Z1 and this harmonic oscillator was there because you have a harmonic oscillator track to begin with.
And roughly what would happen if there are Z1 and Z2?
This one. So what you'll get Z1 double dot is minus omega square Z1 minus Z1 minus Z2 whole cube or something. The Calogero model. Okay. I mean, then if you don't have frequency, it is omega. If omega is 0, then you are going to no potential case, and then Z1 double dot is 0. Sorry? No, the coupling is, yeah, it doesn't, yeah. So, I mean, the equation for Z's and X's are like same.
So but take n equal to n. That's the idea, most of it. Let us look at 100%. Attribute.
Just so I understand, those relations between x's, p's and z's are true for all time, right?
Yes, they're true for all time.
And so you just choose your z
Mm.
0,
Mm.
and then that defines, if you can solve them in a sort of implicit way, the x's and p's.
Absolutely.
And then you evolve the z like this,
Yeah.
say for one soliton, and
Yeah.
keep solving for
Yeah.
x and p's.
But it's
But
just
it's still not very easy to do.
no, but we don't need to keep solving, right? Because once I have X's and P's, I will do my
That's what I wanted to
Yeah.
ask. So the practical way to do it is that you just obtain the x's and p's at
once. Yes.
and then you don't really evolve z like
Yeah,
this.
yeah. Then you don't care about Z.
You know, you do it the other way and
Yeah.
obtain them,
Yeah.
and then it so happens that z is
Yeah, yeah, exactly. And this is the next slide. So
Yeah, and these solutions, does effective action of the Z1 seems to be like Z1 dot square minus omega square Z1. Now, in a soliton which came from symmetry, you will not ever have this omega square Z1 square kind of thing.
Right.
When you put the velocity of the soliton to 0,
Right.
then it goes to a 0 mode. So
Right.
it's an therefore the effective action would vanish.
Right.
So you should have only derivative couplings in an effective action of
I
soliton.
mean, if you didn't have the trap, that's exactly what it is. If you don't have the trap, then you can slide all the x's by an equal amount and nothing changes, but z breaks that symmetry. Right? So 1 over x minus z.
There is some symmetry which is depicted by.
So the case you are, I think the case you are mentioning is exactly the case without the trap, and then z does go like this v times t, like it
Yeah.
The trap breaks your symmetry translational area. Exactly. Otherwise, what you say is essentially
Okay. So this is how it would look.
From that point of view, is there a direct relation that one could write?
Yeah, one could write a lag space for z's.
Are they related in this fashion? Because the way you were evolving it, it
Hmm.
seems very closely, really, you might as well have parameterized it with three variables.
Yeah. Right. So all the z's have their own lag spares, but now you're asking what is this? How does this equation look? The top two equations in the lag spare formalism. Is that the question?
I'm just saying that, you know, the fact that there are solitons in the following certain dynamics,
Hmm.
the question about how the resolution of initial state is taking place. Right?
Hmm, hmm, hmm.
But in the beginning, you also had this projection method which was very useful. It
Right.
seems that the natural, I mean, one would be able to understand
Right.
the existence of these Z from that picture.
Right.
It's very to both ways.
Okay. So yeah. So okay. So this is how it would look, a typical world line diagram. So you can see your soliton going like this. Okay. And here you see that you have a soliton solution, and essentially it is kicking a particle out, and then this particle sort of goes back, goes into the cloud, and just kicks another particle out. Okay. And this is highly non-trivial thing, because usually what happens is that if something just goes, it will just disperse and the thing will just move very randomly. So these are already indicating that these are very finely tuned initial conditions.
Sorry, these are the actual particles?
These are the actual particles. These are the actual particles.
So this is a soliton thing.
This is the soliton solution, yeah.
Consisting of only one. I thought it was some of all done.
No. So this is just finite number of particles. So the lump I make it by just defining 1 over interparticle distance. That will be like a.
Which is the soliton? What is the position of the soliton?
So here, okay. So sorry, the diagram.
Sorry, we just ask one more repeat. So this net soliton is one where only one particle is in effect moving? Is that what you're showing us?
Um,
Is that at rest? Is that what you're showing?
No. Okay. Let me skip of how the collective thing will look. The collective thing would look like this. Sorry. Okay. So it's a lump that is just moving, and then it will just move back and forth like that. Okay. But it can go out of your cloud, and then only one particle gets kicked out. Okay. It was in the cloud. Sorry. So this, see, this thing is going, then it goes inside, then in the cloud they go as a lump, and then they.
So it behaves like the continuum soliton only when the particle hits back.
Yes.
Otherwise it's not.
Otherwise it's like a delta.
Like the continuum soliton.
Yeah. Exactly. So.
But when it is hitting that lump, then x is effectively not changing, right? It's just, I mean, it is redistributing among the different red balls.
Right. No. So no. It is. I mean, when it's you can't see it, but what will happen is that, okay, if you don't have any soliton, it's just a lump, right? So if it comes, it will go like this.
You can see it. You can see that.
You can see it?
Yeah, you can see it here. I'm showing it.
Oh,
I see.
Okay.
Yeah. All right, now I understand.
Oh yeah. So now it's kicked out.
Okay.
Okay. So
It's interesting that the edges get expanded and come down.
right. So this is how it will. So clearly these are special initial conditions. So because usually what happens, the general statement is if I start with an arbitrary profile, then it can just break. Some of them can break into solitons, other will just give waves and so on. So here it's clearly a robust moving solution.
This
So
is with the potential?
this with the potential. That is, yeah.
Without the potential, something like this happens, right? This momentum conservation. I mean, at least I
Without potential, it's just a Lorentzian. It will just go, right?
it never happens. One particle never goes out.
I mean, without a potential, we have to take the limit a bit carefully, right? Because you have, yeah. So and that's the next slide actually. So next slide is okay. Sorry, it's not okay. This is an example where approximately a soliton would look like this. Okay, meaning that there is a lump which is rho 0 of x. If you don't have potential, rho 0 is constant, and then there is a Lorentzian piece. And x and y are basically z is equal to x1 plus I y1. Okay, so that is the thing. Okay, so and this is how it would look. Y controls the width, and x is the, so real part of z is the position of the soliton. Imaginary part is the width of the soliton.
So basically the height and width are correlated.
Yeah. And this is so it's like on top of a curved solution, or on top of this kind of non-zero, non-constant solution, you can have the notion of solitons. Usually when you think of solitons, you think of x minus vt, but now on this kind of background, you can have the idea of a robust solution moving without breaking. So
So this is the solution which you actually get in the continuum movement when you go to the fifth stage?
no, unfortunately, it is not possible to really break it like this. This is like an approximate thing. What you get in the field theory is, you can't break it into background plus a Lorentzian.
And what is this? I thought this was.
This is just more or less how it would look.
Not
Yeah, it's not because it's because the exact solution is very sensitive to all these things, right? So as soon as you break the solution like this, they may not satisfy the exact equations. Exact.
Of course, you have to, that happens even in the standard solitonic thing. That you have to make sure that it's not the usual normal mode expansion, like if the soliton
Yeah.
passed by your old A derive.
Right.
You have to make sure that your soliton is orthogonal to everybody else.
So yeah. No, I will show you the exact solution, and I will show you that putting this doesn't really. I'll show you the equation that needs to be satisfied for the exact solution, and I'll show you that this doesn't satisfy modulo this 1 over n corrections.
It satisfies it up to y.
It satisfies, yeah, at n equal to infinity.
Yeah.
Yeah, but
Oh, I see.
yeah, that's
Okay.
yeah. So I will come here.
Didn't you say that Alexei Polychronakos showed that the Lorentzian is a exact solution in the continuum?
Lorentzian is exact solution in the continuum for the flat, for no potential case. What Gautam is asking is, can you break it into Lorentzian plus a background, a non-trivial background,
In the presence of the potential.
in the presence of potential? That's it. So yeah. But yeah,
The background being the zeros of the Hermite column.
background being the continuum version of zeros of the Hermite column. Yeah.
So that didn't arise because of the trap, right? That part of the.
No, it arises. Yeah, because the zeros of the Hermite polynomial
With the low infinity.
satisfied this equation, right?
I'm sorry.
Okay, so in the quartic case, also we can find the soliton solution. So these are example of one soliton, two soliton solution, and you can see that two soliton solutions. You can see that they are like two of these spaghetti world line solutions here, and this is just one here. Okay, and so the Z now satisfies this equation. Okay, because it is quartic.
Who knows how the coefficients are.
Okay, this we sort of choose. Yeah,
It's not the original trap.
It's not the original trap. Yeah. So there are some subtleties. So but.
But it's possible to choose the parameters of the original trap so that we use the original trap.
Yeah. So what we choose is. Sorry. No. No. 1 second. The original trap and this are exactly same.
Oh.
I chose my original trap also like this.
Oh,
Yeah. Sorry.
I thought you had some more.
Look. It's the same.
It didn't look like it.
No. 1 second.
That's why I was asking.
No.
But that might be an error.
No. It's.
It's well enough. Oh, you're right.
Yeah. There is. Right. So okay. I'll just confirm if it's an error or if there was an additional term. I mean, I'm not sure if this was an error. So. Yeah.
Just out of curiosity, in the harmonic case,
Mm.
I should have paid attention. Are the two harmonic terms the same in x and z?
Yes. Okay. So one thing that we ended up not really being able to solve is that we have this equation. So this is just a minor distraction, but we have this equation of this form. Say for example, of this form, and we don't know if solutions of z are bounded. So that somehow if you have z double dot is minus omega square z, okay, we know that the solutions of z are bounded. But if z double dot is minus omega square z cube, we are not sure if the solutions of z are bounded.
Is there a potential?
It's a quartic well. I mean, how can it?
No. These z's are complex.
Oh,
So
how do you know for the first case that it is bounded?
it is linear equation, no? We can just solve it directly.
You solve it so you know.
Yeah, solve it, you know.
But here you say you don't.
Yeah. If you write it in terms of x plus iy, it's very unclear if it's bounded. It's not a problem for us because we don't really care if z is bounded, because if z goes far away, I mean that soliton is not gone. So x's and x's are well defined. So boundedness of z is not an issue, but generally this is a question that still is unclear. So if z is bounded for.
Because x's are real, you don't have the issue with.
Yes, exactly. Yeah.
That might be another question on duality.
Okay, so yeah. No.
That may not be consistently like this.
Yeah. And so if all are complex, so if you want x's to be real, then there's a constraint on z. Yeah. I'll show you in the next part. See, what do we finally want? We want a real x's having some dynamics. So we want a well-defined, stable, dynamical system in X. That is our.
Like Sandeep said, there is no real duality because physically they look different. Right? The z's can go off to infinity by the
No, but that could be real, then x would be the same.
So one thing is we.
It's like one theory to another rather than theory to another.
Maybe right way is to just even promote the access to the system.
Yeah, so I will do that next. So,
And then I
yeah.
can do.
So there is. I will come. That is the next one. I'll have some water. Yeah. Sorry.
This is one strategy of ours when we are having a tea.
Okay. So the question is now, how can we get these kind of some sort of duality and from a more general structure. So basically,
More general meaning not integrable.
yes, not integrable, but then somehow we end up with integrable models. So
So just to say, what would be really interesting is if you could break the integrability but preserve the real. Well, if you got an integrable system, everything works.
right.
But you know, the really interesting thing about duality is that they're present in non-integrable.
Right. So
I don't know, everything. Okay, what about mathematics? Very new.
so we
Well, and the n equals 1 is very much like carry on version. carry on. Yeah, so some element of
Maybe so we have ended up with some non-integrable models here, and as we increase our requirements to go towards a soliton solution, somehow we have to slowly we start getting integrable models. But the question is whether there is duality before that. I'll just present this and then. So let's consider a.
I guess less, maybe the answer is obviously if you require soliton solutions as defined in some way, are you necessarily left to integrable with all conserved charges?
Yeah.
If you just wanted a well-preserved lump, does it necessarily require?
If you there are non-integrable models which have soliton solutions, but there are only 1 and 2 soliton solutions. So just having 1 and 2 soliton solutions, yeah.
If you want n
Yeah.
solitons, that's
If you have multi, yeah.
And do we include as part of the definition of solitons that they have to go through each other while preserving shape, or we don't include?
They go through each other.
Can there be a notion where you have individual well-defined lumps, but you allow for non-trivial scattering? Well, that's not correct.
Yeah. So if you have Calogero thing.
Calogero, they
Mm.
necessarily.
Yeah.
But they will allow you that. Yeah, they will.
Yes,
So
yes.
So when you say you want n well-defined isolated enough lumps, you allow for the interaction.
Yeah.
And that's enough to require integral.
Right.
Sorry, just one last, because you said something like 1 and 2 doesn't imply it, but once you have 3,
Yes,
something
yeah,
like
yeah,
that,
yeah.
then necessarily.
Yeah. So there's a theorem that says if you have 3, then you can show that you have more than 3, and hence it's integrable.
Is this related to this, what is this thing called, that Young-Baxter, that if you can cross 3 times, then you can do it?
Yeah, it's yeah. So yeah.
one last, just because, just one last. If you take the integrable theory, and then you add a little bit of a non-integrable, let's say interaction particles between the x's, can you translate, can you figure out what that interaction amounts to in terms of results? Just a linear. What? Oh, they are saying the whole question is not there. Yeah. Okay, sorry, yeah.
I mean, solitons will not exist, right? But one thing you can.
Linear or whatever. It should be, right? It is just a small perturbation around it.
But you perturb. What do you want to perturb? You want to add a term in x.
I want a small deformation.
Right.
And see what that corresponds to in terms of the
Right. So yeah, this is hard to, because then you can't even use this projection method and nothing like that. So.
Small perturbation over time, I mean, this is the point, right? Over time, it could build up, right? So
Right.
your thing can break up.
Right. So, yeah.
The fact that you have like diameter that they're not planned direction, if you look at it from the point of view of the gauge state, it corresponds to lifting factor. So when it's breaking any two pieces, taking out any two points in the so maybe an interesting thing to do would be to start off with this systematic gauge state. We know what the integrity is, so we can calculate the system. And then you by hand you put in a potential, like a harmonic factor. And that would lift the modular state. So you get a set 750 points in a given computation. There would still be enough symmetry for something interesting to happen, but it won't strictly be exactly happen.
So the trap for the solitons and the trap for the x's,
Uh-huh.
that's the same. But the mutual interaction between the two solitons, that's also identical?
Yes.
So, I see. So if x's are strongly coupled, then so are the z's.
Yes.
It's like G equals 1.
G equals to 1.
Yeah. So. Okay. So so the thing is that I will start with my first order equations, and let's start with the general first order equations such as x's are all complex. Okay. So this is just understanding the whole previous thing in a more systematic way.
Manas, I'm really sorry, since it's all our fault, but in about 10 minutes if we could finish, then we might have a chance of getting some lunch.
Okay. So let me so let's start with a complex x, okay, which satisfies this first order equation. Okay. Now I can just write x double dot is equal to this. Okay. And so this has the form, there's some potential such that mx double dot is minus del v by del x. Okay. So this is just a general form of first order equation. Okay. And x's are all complex. There is no reality, nothing. Okay. Now I am just imposing that my Phys, which the potential is made of, my Phys is only a sum of two body terms and one body terms. Okay. So this is what I am saying. I am imposing that my phi is a function of only two body terms and one body term. So this immediately gives me del a phi is equal to this, okay, and some constraints on this f's. Okay. So this is clear. Okay. So now if I substitute this into this, my potential takes this form. Okay. My potential takes this form. Remember that this is my potential. X double dot is minus del v by del x. Okay. This is my potential. Okay. So my potential takes this form. And so I can just rewrite it like this. So I have not done anything here. I have just assumed that, let us assume some general pre-potential phi such that your potential takes this form, which is this. Yeah. Some small change of variables to bring the masses in some symmetric form. Okay. Okay. So this is the thing. Now I don't want, this is fine. This is two body terms. Okay. This term is two body term. This is okay. I don't want this term. Okay. This is like a three body term, BCD. Okay. This is a three body term. So notice that I just got rid of W here because W is external potential. Okay. I am just talking about XAB. Okay. So
You got rid because you didn't include it?
yeah, I'll take care of it in next slide. Yeah, zero potential case. When I say zero potential, when I say potential, I just mean mostly external potential, not the interaction. Okay. So then I have this form. Okay. Now I want to make sure that this fellow is only sum of two body terms. Okay. Then that means I have some general complex x's which have some two body dynamics. Okay. I will show you how duality, Calogero models all come out of this. So this is just I'm going in this direction. So instead of sum of two body terms, let me just assume that there are constants. This product is a constant. Just let's assume this product is a constant. Okay. It turns out that if this product is a constant, depending on which constant it is, I generate Calogero terms. Okay.
And those are the only solutions.
These are the, yeah, these are actually uniqueness of these solutions. Yeah, these are the only solutions. Yeah. Notice that this was my most general requirement, that they are just sum of two body terms. You have this sum of three body terms and I want to make it sum of two body terms. And I just made this as a constant. And I get the three Calogero models. Exactly. So Weierstrass, the thing is Weierstrass, we don't have a rigorous calculation yet, but if you assume that this is a sum of two body terms, that would give you Weierstrass. So let me just repeat. So this is my most general requirement. I am just making this constant. Then I get all these three, but this need not be constant. It can just be sum of two body terms, and that would give me Weierstrass.
You can check that for the Weierstrass, it is a sum of two body terms, and probably what you haven't checked is that there's no other one.
So the problem is this is not f is so what is Weierstrass is so
Potential is
yeah. So the point is this is there's some idea, probably some version of Jacobi sign functions which are related to Weierstrass. So this is something we are trying to figure out. Okay. So one thing is, notice that these masses are all random here. Okay. So I'm just generating the Calogero like potential, but with random masses. Okay, so nobody knows whether this is integrable. Okay, we don't know if this is integrable, but our guess is that we have produced some integrable models in the process. At least some limits of these must be integrable. I mean, if all masses are same and if x's are real, then it's integrable, right? That is the Calogero family. So we want to, again, we start with some general pre-potential, get some general form of potentials, just say that particles, at least the potential has only two body terms or one body term, not three body terms, and see what kind of, so again you get these addition theorems. These are different sort of addition theorems, okay? And then ask what forms of those functions satisfy this requirement. If you put this quote hyperbolic into this, you will see that you will get plus g square. Okay, so that is, so I mean this the proofs of this are a bit long, but you can show it's fine. Okay, so this is one thing. Now with potentials. Now with potentials, notice that I already had this and this term. Now with potential I have just extra term here. Okay, this is with external potential. Okay, and again if I want to require that this is sum of only two body terms or one body term, then I get these equations. Okay, I am going to take the this term to be 0, but I'll justify it in the next slide. Okay, I mean I can restrict myself further and further. Okay, because this is the most general situation. But if I take this, then this is what I get. Notice what I get. I get wx up to x square, which means that my external potential is 4th order polynomial, and I get this. All these three for equal masses are integrable. Okay, so just by starting with most general form of potential and imposing requirement of two body potentials or one body potentials, one body terms, and then making masses equal, I can just generate these external traps. So it turns out that all these are integrable. So for equal masses.
But for unequal, it's an interesting question. You haven't been able to construct the lax pair and so on.
Yeah, for unequal, yeah, it's not clear if it's actually even this. So remember, wx more or less wx square is like your potential, right? So this is like x power 4 polynomial. But whether it is integral for higher order polynomials is also an open question. So that is so yeah. So basically, okay. So this is the thing. Now till now we assume that all x's are complex. Okay, all x's are complex. Now our goal is to find a subset of particles that will remain on the real line. Okay, that is our goal. We want among all these complex numbers, we want a subset that will remain on the real line. And by I mean, if all remain, then we'll have no solitons. I'm trying to make this argument that you have all these particles. I will impose the subset to be on the real line, and the remaining will act like the soliton parameters.
But in the physical context, did you know that all x's were real or not?
No, we didn't assume anything. No, we didn't.
In your equations you have it. But if you want, I mean, if you want to define a system with n degrees of freedom, then x's were real.
Then x's were real, yeah.
But you say this well-defined dynamical system, even that.
I think what you will say that the ones that require to be real are going to be a position. The rest are going to be positions from the solid.
But what was in the microscopic theory, were there some x's that were real?
The fundamental particles.
Yeah.
The positions were taken to be real.
Yeah.
But then, I'm trying to because I'm not understanding why you're allowed to have some x's.
No.
These are not going to be excess of the previous thing.
Right. These x's have nothing to have nothing to do with the previous part of the talk. Okay. These are just some complex x's with some dynamics. Okay. These x's have nothing to do with Calogero particles. Okay. So they're all complex, but the question is, if they're all complex, they will not describe anything. Now I want some of them to be real, and have some stable dynamics between them. Okay. So first of all, to do that, we have to make some transformations to make sure that the potential is stable. And if all particles are initially on the real line, then they will escape to imaginary axis. So notice, this is a very interesting point. xi dot is this. Okay, xi dot is this. Imagine all x's were real. Okay, then xi dot will make them escape the real line. Okay. Okay. So therefore we want some of them to be real and some of them to be complex. Okay. Is that so? Okay. So some of them. So we will call n of them real and m of them complex. So total I have n plus m particles. Okay. So this is the equation which says that if they are initially on the real line, then they will escape to imaginary axis. Hence we cannot have all particles on the real line. So we hope that some complex numbers will make these fellows remain on the real line. Okay. So that is the.
Your small n here is actually capital N. Is that
This small n is capital x1 to xn, n plus m or something. Yeah, n plus m. So I just relabeled for clarity. So okay. So then if I do that, let me label the real particles as I and the complex numbers as alpha. Okay. Then you basically have these equations. Okay. Now notice that if I want no coupling between x and z, then I have to have this condition satisfied, this condition to be satisfied. Okay. So only possibility is that all masses, all mj's are m and m alphas are minus m. So basically solitons have negative mass in this formalism. Okay. And if uj alpha is 0, then you can show that this term doesn't exist. So basically at the potential level they are all decoupled, which is what we wanted.
Really sorry, but we're in danger of missing lunch.
Okay. So let me. Yeah. Okay. Okay. No. So I'll just take 5 minutes. So I'm almost done actually. So okay. So this is basically we can show that all solitons in this formalism have negative mass. So that is the thing. And then this is basically saying that this is basically saying that you can impose reality conditions on this x, and imposing reality conditions of velocity gives you these equations. These are the same kind of equations I had in my previous slide. So the real particle system follow a motion parameters by m complex solitons, and solitons obey their own dual Calogero system. Okay, so this is my last slide, I think. So this is basically the continuum limit of Calogero model. So you can show that the continuum limit of Calogero model is like this, where rho and v have this canonical delta prime commutation relation. Okay, and notice that you have this Hilbert transform here and so on, and log terms. So this theory is exactly integrable. This is integrable. So this has infinite integrals of motion. Okay, the continuum theory you can study in itself, and it is integrable. So.
Wait, so now this is a local.
No, it's you have rho h here. Yeah, so it's a non-local theory. Okay, so Hilbert transform. Yeah. So you can naively argue how each of these terms comes, but you have to do the continuum version very carefully, because even if you miss one term, you lose integrability.
Right.
So to take continuum limit of a discrete integrable model is very complicated, and in this case it can be done. So these are the solutions for the ground state. So this will. So this is what Shiraz was asking, and basically the ground state is when the density field satisfies this equation, velocity field is 0. So notice that if I didn't have this log term, then actually just semicircle is the exact solution of this first equation. And because I have this log term, I basically have some corrections. Okay, is that clear? So this is what I would call a row background solution. And this is my one soliton solution. Okay, so this is my one soliton solution, and now to answer Gautam's question, notice that this is I give you my z, okay, and this is how my continuum soliton solution would look like. Now the question is whether rho equal to rho background plus delta plus Lorentzian would satisfy this. I am not I'm not fully sure, but this is essentially how it would. This is the exact answer. This is the exact answer. Exact answer. If I ignore Lorentzian here and do some things, then maybe I can show something. But this is the exact answer, and it basically looks like this background plus Lorentzian. Okay, so but if you substitute it, it will not satisfy. So yeah, and the velocity profile will be just Lorentzian. Okay, so I'll just stop here. So basically, we exploited the structure of integrability to find solitons and perform nonlinear dynamics. Then notion of solitons on curved solutions, curved background solutions, and soliton solutions both for finite number of particles and in the hydrodynamic limit. So driving integrable models is a very interesting direction. What happens when you drive, and does it heat up, and so on and so forth. So those are the things, and possibility of soliton solutions in elliptical cases is and generalized cases we are not we are still working on, and question is, can we generate more integrable models and do something more with this duality, or yeah, these are the things we want to do. Yeah, right.
When you did this analysis of Soliton intersected theory from fractal, how it's like Calogero, did you also do it for the circular motion, the trigonometric Calogero?
Yeah. For trigonometric algebra, all this should go through. So basically, what will happen is that you can which part for
I was going to ask if the solitonic theory would also be a trigonometric Calogero.
yeah.
So is the radius of the circle 1 over radius of the circle? Because I would imagine we have to put it in the torus, so the row function. Elliptic one is probably the more going there, and the tau appears naturally the parameter that torus. Tau goes minus 1 over tau. So I was just trying to see when you were doing that. In particular for a circle, it should go probably to 1 over.
What?
The radius of that circle, the first circle, in the solitonic picture should go to 1 over radius I thought.
For in the Z.
In the
Yeah, I don't remember on top of my head.
The R goes to the infinity limit of the circular case, the line case.
Yes, I think so.
But then since line goes to line, it suggests that.
Yeah. R goes to infinity is the line case. Yeah.
HRI, any questions?
There.
No. Anirban, do you have any questions? Right. Okay. Wait. Two quick questions. Firstly, you said something about fractional statistics. Just take 2 minutes more. 1 minute more.
So basically, if you take the quantum problem, so if you take the okay, this I don't know much about actually. So I mean, basically, you don't have neither fermion statistics nor bosonic statistics, but because of this lambda, this coupling constant, you have yeah. So I mean, yeah, I don't know much. I mean, I don't I'm not, yeah. But basically, you don't have your ground state wave functions, I believe, don't have fractional statistics.
But is this just some statement about ground state wave functions, or is something more complex?
It's
2 plus 1 dimensions together with unknown Bohm phase, you have anions, which are
right.
fundamentally characterized of the particle.
Right.
Something like that? Or?
Yeah, probably it is some. Yeah. It's not just. I mean, yeah.
Okay. One more question. You have this duality between the particles and the soliton.
Yeah.
What is the relationship between the particles and the soliton in the case n equals 1? Is that well defined?
If you have n equal to 1, then you just have one integral. I mean,
the theory itself is trivial, I know. So can you do your solitonic transform in that?
no, yeah. So if you have n equal to 1, then you basically don't have no terms here. You just have xj dot minus I omega xj equal to 0. They just completely decouple, no?
So there's no solid, there's no z.
There is no z. There is no z, right? Yeah. No, sorry. You have a z. So 1 over x1 minus z is there.
So already that's a non-trivial.
Yes.
Already for
Yeah.
just the particle in the potential,
Hmm.
you have a non-trivial transform
Yeah.
that takes you back to the particle in the potential.
That's correct. Seems so that. Yeah.
This is something one can check through elementary.
Right. Right. So basically what we have is x minus I omega x equal to 1 over x minus z, okay? And then z minus I omega z equal to 1 over I guess x minus z, because yeah.
Can I think of the first equation as defining the relationship between x and z, even in the quantum level? I was just wondering whether I took the quantum Hamiltonian
Yeah.
and I rewrote it in terms of z defined this way.
Right.
Will I get back the same Hamiltonian in terms of z? Doesn't seem entirely obvious.
Right. Not.
But it sounds already like you might have an interesting quote unquote x duality
Huh.
of a very simple.
Right. So in the classical case, I guess it's right. I mean,
And then the next thing I would study carefully is n equals 2.
right.
I mean, just to understand, if there is this nice duality.
Right. I mean, so how do you suggest to, because if you have this equation solved for z, in principle
It doesn't
you
look
can.
like I don't understand. You understand much better than me. But if I can think of the first equation as something defining z as a
Yeah.
function of x,
Yeah.
then that gives me, now it doesn't look like, right? You've got a potential in terms of x.
Yeah.
If I just rewrote that in terms of z, it looks like it would go to all orders.
That's right. Yeah.
But maybe the kinetic term also goes to all orders. And then, so I don't know what.
Yeah. So it's
How does it work? How does the duality work?
right.
And n equals 1. This should be trivial.
Right. I mean,
already help us understand what the nature of the duality is.
right. No, but
Unless I'm saying something.
but I mean the point is, if I take one more derivative, then I decouple, right? So I mean the question is, if I don't, so sorry.
So, but I'm interested in the map of variables. You
Right.
Two different systems.
Right.
In both cases, you take one more
Yeah.
you decouple.
Yeah, but if you
So
yeah.
Z behaves like a particle in a potential.
Yeah.
Potential x behaves like a particle in a potential.
Right.
But you use either the x description
Right.
or the z description.
Right.
You're not supposed to use both.
Right.
So the interesting thing is the transform between.
Right.
Later part of the thing, both these variables and more, the coupling between them vanishes.
Yeah.
No. Coupling between them in the second order. In the potential, in V of x, they don't couple. In the first order, they couple. Okay, I accelerated a lot in the later part of the talk, but right. So remember, V of x is decoupled, right? So
That kind of understanding would also be necessary, rather than something that is very, very democratic.
no, but that's what we try to do in the later part.
Oh, you're saying x is just the answer. You're probably.
Sorry, but we have to be careful.
So then the x is then sign.
We have to care. Yeah, I think what we have is x dot. No, we also have this. I don't know what is how to write, but sorry. Yeah.
So the x minus z obeys some harmonic equation.
Yeah.
It's not clear. Yeah, but it's not clear. It's 0. X minus z obeys the equation x minus z dot minus I omega x.
So u dot minus I omega u is equal to 0.
Yeah. Now, it's not clear that sets this to 0. And if you set it to 0, that means the right hand side very big.
Yes, it does. So, you know all the solutions in x minus z.
You know all the things.
You know the solutions. The other one is there.
Then you have to figure out what
Right, right. No,
That's why kinetic terms is infinite number of terms, because this x minus h is some known function. So means to become I therefore infinite number of terms.
I see. Okay, one last question. In this hydrodynamic theory, is it like a dissipative theory or not?
no, no. This is no non-dissipative.
It's non-dissipative completely. So, you know, if you keep track, I'm saying something very basic. If you keep track only of the action degrees of freedom and not the angle degrees of freedom, is there a way of getting, here you're keeping track of everything, is this right?
Here you're keeping track of everything.
So
Yeah.
somehow you integrate out the angle degrees of freedom.
Then you might get
You might get an
yeah,
effectively dissipative
yeah.
system.
Then you'll get effective dissipative system.
I was wondering whether that would be possible to do practically.
Uh,
The kind of thing Gautam keeps saying.
so is it like I mean, but why? But here also you're just saying why don't you integrate out one of the
It's like getting rid of
rho or v or something, right?
is
Yeah.
that, you know, I was wondering whether you could see some effective description in terms of half of the degrees of freedom that would show you normalization.
Right, right, right.
I mean, Gautam's beautiful calculation showed that.
A subset of
Right.
the
Right, right.
And it has to include all the conserved quantities.
it has to include all of it.
So then half of it.
Yeah.
So if you keep all the action degrees of freedom, throw away the angles. As the angles evolve, oh no, maybe the others, I don't know. Sorry, maybe the others. I don't know, I'm sorry, I'm sorry.
But I mean, so
Maybe
so here
some sort of smearing over the angle degrees. You want some physical quantity smeared over angle degrees.
Because
Right.
the angles are all, in my case, you know, the angles are not the final degree of freedom.
Yeah,
Mhm.
complicated. This
Mhm.
projection, this projection.
My angles are all in real space, whereas these guys are all in angle variables are all in fluid space.
Yeah, so maybe the question is something like the density of these particles, the physical density of these particles. Try to find some effective equation
for the
showing just the physical density of particles and nothing.
No, I mean, okay, the one I told you, Benjamin Arnold, their soliton solutions, the guiding centers were Calogero, but physical, no, Benjamin Arnold is also not dissipative. Benjamin Arnold is not dissipative. So by what Shiraz is saying, you should probably get a dissipative.
Something,
yeah,
it's
you
just
should get it.
information because you're
Yeah.
keeping only
Yeah.
half the degrees of freedom.
Yeah.
You need as many degrees of freedom as conserved quantity. That's the general rule of thumb.
Right, right, right.
So it sounds like keeping all positions is the right thing. Right.
Right. But then they'll have, no, but what will be the conserved quantities?
The conserved quantities, yeah.
Will also be infinite because the system is infinite, right?
But the conserved quantities were in terms of
Wi-
positions
and-
and angle depth.
Yeah, yeah,
So now you lose that information.
yeah. So you have a separate equation completely in
Yeah,
just a row.
You're
Yeah.
trying to derive hydrodynamics with this very beautiful, simple system.
Right, right, right.
You might expect that there is, in some approximation, in some way, you
Right.
can get an equation just for the densities of particles and
Right.
nothing else.
Right, right.
And,
Yeah.
and maybe that will show dissipation, and maybe you can use that to understand the problem.
Right. I mean, not for this, but there are other models in which we do this, where you do something called adiabatic approximation. Like you sort of assume that some fields are moving slowly than the other, and then you substitute the solution of one field into the other, and then you'll get some effective equation in one field. But here, I mean, that's one thing. If you assume that the V is varying very slowly
Yeah.
compared to rho,
Yeah.
then you can separate them.
It's a big question. I don't
Right,
even
right,
know.
right. So yeah, yeah. Also, if it's dissipative, will it retain integrable? I mean, if it's actually, you never know. I mean, there's some of
You know,
No,
what
it's
I'm
in
calculating.
the full system it is integrable, of course. But it's just because you were
Yeah.
you were focusing on a subsystem.
yeah, but then you may actually break integrity completely, because if it's dissipative, then maybe something very trivial is conserved, like integral of rho or something may be conserved. But
All the integrals are still conserved. It's just that the system looks dissipative because you were integrating.
right.
The include contributions of the single nature.
Okay, then yes, but okay. Yeah. This is-